Welcome to this comprehensive lecture on microfluidic fuel cells, an exciting frontier in energy conversion technology. Microfluidic fuel cells combine microscale fluid dynamics with electrochemical energy conversion, creating efficient, portable power sources. Let's begin by understanding the fundamental concept of microfluidic fuel cells. Microfluidic fuel cells are electrochemical devices that operate at the microscale, typically with channel dimensions between 10 micrometers and 1 millimeter. Unlike conventional fuel cells, they often don't require expensive proton exchange membranes because laminar flow at microscale prevents fuel and oxidant mixing. The Reynolds number determines flow regime. At microscale with low Reynolds numbers, typically below 100, flow remains laminar and predictable. Here we see laminar coflow in a microfluidic channel. The fuel and oxidant streams flow side by side without turbulent mixing, separated by a diffusion interface. Now let's explore the electrochemical reactions that power these devices. At the anode electrode, fuel molecules, like hydrogen or methanol, are oxidized, releasing electrons that flow through an external circuit. For hydrogen fuel, the anode reaction is hydrogen gas yields 2 protons plus 2 electrons. This is the hydrogen oxidation reaction. At the cathode, oxygen is reduced by combining with protons and electrons to form water. This is the oxygen reduction reaction. The overall reaction combines hydrogen and oxygen to produce water, releasing electrical energy in the process. The Nernst equation is fundamental to understanding fuel cell voltage and efficiency. The Nernst equation, E equals standard potential minus RT over NF times natural log of reaction quotient, where R is gas constant, T is temperature, N is electron number, and F is Faraday constant. For hydrogen-oxygen fuel cells, the standard cell potential is 1.23 volts at 25 degrees Celsius under standard conditions. Mass transport is critical in microfluidic fuel cells. Let's examine the 3 main mechanisms. Diffusion is the random molecular motion driven by concentration gradients. It's the primary transport mechanism in microfluidic systems. Fick's first law describes diffusion. Flux J equals negative diffusion coefficient D times concentration gradient dC dx. Let me give you some numerical estimates for diffusion coefficients. Hydrogen in water has a diffusion coefficient of about 4.5 times 10 to the minus 9 square meters per second. Oxygen in water diffuses at approximately 2.1 times 10 to the minus 9 square meters per second. This diagram shows diffusion at the fuel-oxidant interface. Molecules move from high to low concentration regions, creating the reactive zone where electrochemistry occurs. Convection is the bulk fluid motion that carries reactants to the electrode surfaces. Convective flux equals velocity times concentration. This dominates in the channel center away from walls. Migration is the movement of charged species in an electric field, important for ionic transport. Let's examine the critical parameters that determine fuel cell performance. Current density, measured in amperes per square centimeter, indicates how much power the fuel cell generates per unit electrode area. Current density I equals total current I divided by electrode area A, typically expressed in amperes per square centimeter. Microfluidic fuel cells typically achieve current densities between 10 and 100 milliamperes per square centimeter. Power density measures the total electrical power output normalized by volume or electrode area. Power equals current times voltage, or equivalently, current density times area times voltage. For practical applications, power densities exceeding 50 milliwatts per square centimeter are desirable. Fuel utilization efficiency indicates what fraction of supplied fuel is actually converted to electricity. Fuel efficiency, ETA, equals current over NFQ fuel times fuel concentration, where Q fuel is the volumetric flow rate. This polarization curve shows voltage decreasing with current due to losses, while power density peaks at intermediate current, defining the optimal operating point. Real fuel cells suffer from various losses that reduce voltage below the theoretical value. Let's examine these. Activation overpotential represents the energy barrier that must be overcome to drive the electrochemical reaction at a finite rate. The Butler-Volmer equation gives activation overpotential as RT over alpha NF times natural log of current density over exchange current density. Exchange current density, which indicates reaction kinetics, typically ranges from 10 to the minus 3 to 10 to the minus 6 amperes per square centimeter. Ohmic overpotential arises from resistive losses as current flows through the electrolyte and electrode materials. Ohmic overpotential equals current density times total resistance, following Ohm's law. Concentration overpotential occurs when mass transport cannot supply reactants fast enough to maintain concentration at the electrode surface. Concentration overpotential equals RT over NF times natural log of limiting current over limiting current minus actual current. The actual cell voltage is the theoretical voltage minus all three overpotentials. Cell voltage equals standard potential minus activation overpotential minus ohmic overpotential minus concentration overpotential. Channel geometry critically affects performance. Let's explore design principles. Y-shaped and T-shaped channels are the most common configurations for creating laminar co-flow of fuel and oxidant streams. The Y-shape provides smooth merging of two streams, while the T-shape creates perpendicular junction. Both maintain laminar co-flow downstream. The channel width, typically 100 to 1000 micrometers, determines the diffusion layer thickness and residence time. Diffusion layer thickness delta is approximately the square root of diffusion coefficient times time. Residence time equals channel length over average velocity. This must be sufficient for reaction completion. Here's an important question. What happens if we increase the flow rate too much? If flow rate is too high, residence time decreases. Reactants pass through before complete conversion, reducing fuel efficiency. The optimal flow rate balances high fuel conversion with adequate mass transport to maintain high current density. Electrode materials and catalysts are crucial for achieving high performance. Noble metals like platinum, gold, and palladium are excellent catalysts due to their high activity and stability. Typical platinum loading ranges from 0.5 to 4 milligrams per square centimeter. Higher loading increases cost but improves kinetics. Carbon-based materials like graphite, carbon paper, and carbon nanotubes provide excellent conductivity and large surface area. Increasing electrode surface area through porous structures or nanostructuring dramatically enhances current density. Roughness factor equals real surface area over geometric area. Values of 10 to 1000 are achievable with nanostructured electrodes. Nanostructured electrodes with catalyst particles provide enormous surface area and compact volume, enabling high current densities. Different fuels offer various advantages. Let's compare the main options. Hydrogen offers the highest gravimetric energy density at 142 megajoules per kilogram and produces only water as product. Hydrogen energy density is 142 megajoules per kilogram, far exceeding most other fuels. Methanol is liquid at room temperature, making it easier to store and handle than gaseous hydrogen. Methanol oxidation. Methanol plus oxygen yields carbon dioxide and water, releasing 6 electrons per molecule. Methanol energy density is 22.7 megajoules per kilogram, lower than hydrogen but still substantial. Formic acid is safer than methanol, non-toxic, and exhibits favorable electrochemical kinetics on platinum catalysts. Formic acid oxidation yields carbon dioxide, 2 protons, and 2 electrons. It's a 2-electron process with fast kinetics. Glucose and other biological molecules enable biocompatible fuel cells for implantable medical devices powered by body fluids. Let's work through a numerical example to understand typical performance. Consider a microfluidic fuel cell with the following specifications. Channel dimensions: 500 micrometers wide, 100 micrometers deep, and 2 centimeters long. Operating current density is 50 milliamperes per square centimeter. Cell voltage is 0.5 volts at this current density. Let's calculate the total power output from this device. Electrode area equals width times length. 0.05 centimeters times 2 centimeters equals 0.1 square centimeters. Total current equals current density times area. 50 times 0.1 equals 5 milliamperes. Power equals current times voltage. 5 milliamperes times 0.5 volts equals 2.5 milliwatts. Power density equals power over area. 2.5 milliwatts over 0.1 square centimeters equals 25 milliwatts per square centimeter. This 25 milliwatts per square centimeter is representative of current membraneless microfluidic fuel cell technology. Let's quantify the relationship between flow rate and efficiency. Continuing with our example, let's calculate the fuel utilization efficiency. Assume flow rate of 0.1 milliliters per minute, which equals 1.67 times 10 to the minus 9 cubic meters per second. Hydrogen concentration in aqueous solution is approximately 0.8 millimolar, or 0.8 moles per cubic meter. Molar flow rate of hydrogen equals volumetric flow rate times concentration, 1.33 times 10 to the minus 9 moles per second. Maximum theoretical current equals number of electrons times Faraday constant times molar flow rate. Maximum theoretical current is 257 milliamperes if all hydrogen is converted. Fuel utilization efficiency equals actual current over maximum current. 5 over 257 equals 1.9%. This low 1.9% efficiency might seem wasteful, but it ensures excellent mass transport and high current density. It's a design trade-off. Understanding the diffusion zone is critical for predicting crossover and efficiency. Let's estimate how wide the diffusion zone becomes as fluids flow through the channel. Diffusion layer thickness equals the square root of diffusion coefficient times residence time. Average velocity equals flow rate over cross-sectional area, 0.033 meters per second, or 3.3 centimeters per second. Residence time equals channel length over velocity, 2 centimeters over 3.3 centimeters per second equals 0.6 seconds. Diffusion zone thickness equals square root of 2 times 10 to the minus 9 times 0.6, which gives 35 micrometers. The mixing zone of 35 micrometers represents only 7% of the 500 micrometer channel width, confirming good separation. This shows the thin diffusion zone growing along the channel. Most of the channel maintains pure fuel and oxidant streams. Temperature significantly influences fuel cell performance through multiple mechanisms. Increasing temperature accelerates electrochemical reaction rates by providing more thermal energy to overcome activation barriers. Exchange current density follows Arrhenius behavior, exponential of negative activation energy over RT. Electrochemical reactions typically have activation energies between 40 and 80 kilojoules per mole. With these activation energies, a 10-degree temperature increase can double reaction rates. Diffusion coefficients increase with temperature according to the Stokes-Einstein relation. Diffusion coefficient is proportional to temperature over viscosity. Both factors increase D with temperature. Most microfluidic fuel cells operate between 20 and 80 degrees Celsius, balancing performance with material stability. Microfluidic fuel cells enable diverse applications. Let's explore the main ones. Portable electronics like phones, laptops, and wireless sensors can use microfluidic fuel cells for extended operation without grid power. With liquid fuels, energy densities of 300 to 500 watt-hours per liter are achievable, exceeding lithium batteries. Medical implants, like pacemakers and drug pumps, can harvest power from glucose in body fluids using biocompatible fuel cells. An implantable fuel cell device can generate power continuously from body chemistry, eliminating battery replacement surgeries. Microrobots and tiny drones benefit from compact, high-energy density power sources that microfluidic fuel cells provide. Lab-on-chip devices can integrate fuel cells to provide onboard power for pumps, valves, and sensors without external connections. Remote environmental sensors and Internet of Things devices can operate for months or years on small fuel cartridges. Let's review exciting recent advances in microfluidic fuel cell technology. Three-dimensional printing enables electrodes with precisely controlled porosity and surface area, improving mass transport and reaction kinetics. Researchers are developing non-precious metal catalysts based on nitrogen-doped carbon, metal oxides, and enzymes to reduce cost. Replacing platinum with earth-abundant catalysts can reduce electrode cost by 90% while maintaining reasonable performance. In conclusion, microfluidic fuel cells offer a promising solution for portable power generation. Thanks for joining me on this journey into the world of microfluidic fuel cells. If you have any questions or topics you'd like to explore further, please let me know in the comments below.